In this video, I'd like to talk about VSEPR theory. Molecular polarity is a slightly separate topic that I decided to put off to the next video. So this video is pretty much just on VSEPR theory. Molecular geometry is the three-dimensional structure of a molecule or polyatomic ion. And if we want to quantify the precise structure of a molecule, we need all of the bond lengths in picometers and all of the bond angles in degrees. However, in this video, we're going to be focusing on a qualitative description of molecular geometry using a word or phrase. And we will use a theory developed in the early 20th century called VSEPR theory, which stands for valence shell electron pair repulsion theory. And the idea is quite simple. Groups of electrons, which include bonding groups and unshared groups, in the valence shell of the central atom repel one another because they're made up of electrons. And they push the groups of valence electrons as far apart from each other as possible. The geometry of the molecule or ion is determined by minimizing this repulsion. The procedure is quite simple. Step one, draw the Lewis structure. You got to know how many groups of electrons you have around your central atom before you can determine how they repel each other. Count the bonding groups of electrons, which we will represent as B, and unshared groups of electrons, which we will represent as E, around the central atom. And then we will assign it a molecular type using the ABE designation. A, B sub x, E sub y, where x represents the number of atoms bonded to the central atom, that would be the bonding groups of electrons. Y represents the number of lone pairs on the central atom. Then, based on getting those groups of electrons as far apart from each other as possible to minimize repulsion, you name the geometry and specify the bond angles. So let's systematically work our way from simpler to more complex molecules. Let's consider molecules that have only two groups of electrons around the central atom. We'll classify that as an AB2 type molecule. Carbon dioxide is a good example. Notice it doesn't matter that the CO bonds are double bonds. No matter how many electrons are shared, the bonding group of electrons behaves as a unit. The bond angle between the two CO bonds is 180 degrees, and we will call this a linear geometry. On the other hand, if I have three groups of valence electrons around the central atom, for example in boron trihydride, in order to stay as far apart from each other as possible, those bonding groups of electrons will point towards the corners of an equilateral triangle, making a bond angle of 120 degrees. Our name for this geometry is trigonal planar. The three groups of bonding electrons are in a trigonal plane with an angle of 120 degrees. The next example would be an AB2E type molecule, an example being sulfur dioxide. Here we have two bonding groups of electrons around the central atom and one lone pair. The angle between the two bonds, again, is 120 degrees. We will name this a bent geometry. Now let's consider molecules that have four groups of valence electrons. If there are four bonded atoms and no lone pairs, I'll classify this as an AB4 type molecule. Methane or CH4 is a good example. In order to stay as far apart from each other as possible, we now can no longer have a two-dimensional geometry. We must have a three-dimensional structure. It turns out to minimize repulsion, the four bonded groups of electrons, as designated in this diagram, point towards the corners of a tetrahedron. A tetrahedron being a four-sided object in which each side is an equilateral triangle. Therefore, we will name this tetrahedral geometry, and the bond angle is 109.5 degrees. If we replace one of those bonded atoms with a lone pair to obtain an AB3E type molecule, as is the case with ammonia NH3, we now no longer call it tetrahedral, but instead trigonal pyramidal, because the four atoms form a trigonal pyramid. If I replace another bond with a lone pair, as is the case in water, I have an AB2E2 type molecule. The four electron groups still point towards the corners of a tetrahedron, but now because I only have two bonds, I'm going to call this a bent geometry. And the bond angles in trigonal pyramidal and bent are also 109.5 degrees. Notice that there are two types of geometries that are referred to as bent: AB2E, two bonds and one lone pair; AB2E2, two bonds and two lone pairs. They have different bond angles, but they're both also referred to as bent geometries. Here's a picture that illustrates the difference between a tetrahedral geometry and a trigonal pyramidal geometry. In ammonia, NH3, the 4 groups of electrons around the nitrogen all point towards the corners of a tetrahedron. However, 3 of them are bonds and 1 is a lone pair. Therefore, we call the geometry trigonal pyramidal. Similarly, in water, an Ab2E2 type molecule, the 4 groups of electrons around the oxygen all point towards the corners of a tetrahedron. Only 2 of them are bonds and 2 are lone pairs, so we call the geometry bent. Now let's move on to our hypervalent molecules, those in which the central atom has more than an octet. AB5, there are 5 groups of electrons around the central atom, all of them bonds, and you may ask yourself, how do they arrange themselves to stay as far apart from each other as possible? Well, interestingly, of the 5 bonded atoms, 3 of them are in a trigonal plane. The remaining 2 form a linear arrangement that is perpendicular to the trigonal plane. So you can see here I've got this fluorine, and this fluorine are in a trigonal plane. The fluorine at the end of the wedge is meant to be pointing out of the plane of the board towards you. The one at the end of the dashed bond is meant to be going away from you into the board. This geometry is referred to as trigonal bipyramidal because you can think of it as being a bipyramid, 1 pyramid on top and 1 on the bottom. The 2 positions are referred to as axial and equatorial. So the 3 in the plane, in the trigonal plane, are referred to as the equatorial positions, and the 2 in the linear arrangement perpendicular to that are referred to as being in the axial positions. The equatorial bond angle is 120 degrees, consistent with a trigonal plane, whereas the equatorial axial bond angle is 90 degrees. Now, we're going to begin systematically replacing the bonded atoms with lone pairs, and the question is, do I replace an axial or an equatorial position with a lone pair? Well, it turns out that because the equatorial positions are further apart from each other, 120 degrees, as I progressively replace the bonded atoms with lone pairs, I will replace them in the equatorial position. So, for example, an AB4E type molecule, tellurium tetrachloride, notice that I replaced one of the bonded atoms in the equatorial plane with a lone pair. This, interestingly, is called a seesaw geometry. As before, the equatorial bond angle is still 120 degrees, and the axial equatorial bond angle is still 90 degrees. If I replace a second bonded atom with a lone pair, it will also go into the equatorial plane. An example of that would be chlorine trifluoride. Notice that now I still have my 2 fluorines in the axial positions, but I only have 1 remaining in the equatorial position. The other equatorial space is taken up with lone pairs. This is referred to as a T-shaped geometry. The bond angle is 90 degrees. And then finally, if I replace the 3rd equatorially bonded atom with a lone pair, I see I now have 3 lone pairs in the equatorial plane. The only 2 remaining atoms are axial with an angle of 180 degrees, and this geometry is referred to as a linear geometry. Now let's look at molecules with 6 groups of valence electrons. How do you get 6 bonded atoms as far apart from each other as possible around the central atom? Well, as we see in sulfur tetrafluoride, there really is only one way to do it, and that is to have bond angles all of exactly 90 degrees. Okay? Imagine, if you will, that the sulfur is in the center of a cube, and each of the bonded atoms is in the center of one of these 6 faces of the cube. If you were to imagine that this is a solid object, it would have 8 faces, each of which is an equilateral triangle. That object is called an octahedron, so the name of this geometry type is octahedral. So anytime you have an AB6 type molecule, the geometry is octahedral. Consider replacing one of the bonded atoms with a lone pair. Well, all of the octahedral positions are exactly identical, so it really doesn't matter which one you replace. An AB5E molecule, like bromine pentafluoride, would look like this. You see that you have 4 fluorine atoms in a square plane with 1 pointing up. Bond angles, again, are all 90 degrees. This geometry is referred to as a square pyramidal geometry. Our final example, an AB4E2 molecule, Well, obviously, we want to replace one of the bonded atoms not in the plane, but opposite. Xenon tetrafluoride will be an example. We have 4 fluorine atoms in a square plane with a lone pair on the top and on the bottom. Again, bond angles of 90 degrees. This is referred to as square planar geometry. So, a lot of information, so let's summarize. If we have 2 electron groups around the central atom, it's an AB2 type molecule with a linear geometry. If we have 3 electron groups around the central atom, there are 2 options, AB3 trigonal planar, AB2E bent. If we have 4 electron groups around the central atom, we have 3 possibilities, AB4 tetrahedral, AB3E trigonal planar, trigonal pyramidal, and AB2E2 bent. For our hypervalent geometries, if we have 5 electron groups around the central atom, AB5 is called trigonal bipyramidal, AB4E is called seesaw, AB3E2 T-shaped, AB2E3 is linear, and then finally, if we have 6 electron groups around the central atom, AB6 octahedral, AB5E square pyramidal, and AB4E2 square planar. I found a nice diagram on the internet that might be helpful. This sort of systematically shows the possibilities in a chart-like form. In this chart, they refer to the number of electron-dense areas, which I would simply call groups of electrons around the central atom, 2, 3, 4, 5, and 6. I've never used the term electron pair geometry, but basically it's stating how those electron groups are related to each other. And you can see with 2 it's linear, with 3 it's trigonal planar, with 4 it's tetrahedral, with 5 it's trigonal bipyramidal, and with 6 it's octahedral. So with 2 electron groups we have linear. With 3 electron groups we can have trigonal planar or bent. With 4 electron groups we can have tetrahedral, trigonal pyramidal, or bent. With 5 electron groups we can have trigonal bipyramidal. They call it sawhorse. We use the term seesaw. It means the same thing, T-shaped or linear. And with octahedral, we can have octahedral, square pyramidal, or square planar. The last 2, AB3E3 and AB2E4, I've never included because I don't know of any examples of those. So that's our summary of VSEPR theory, and in the next video we will talk about molecular polarity.